For this video, we're going to talk about Gibbs free energy. We previously saw a very important concept coming from the second thermodynamic law, which was entropy. That crazy movement of the particles is something that is going to be very useful for this definition. So, what's Gibbs free energy? Well, I put here three definitions that I think that are very helpful to understand it better. So, we first want to see the equation of Gibbs free energy, which basically is a difference between two energies. So in first we know that it's the energy available for a change. That energy available, it's the result of the difference between the total free energy change for a system and the energy that gets lost while it's underneath it. So that difference, the energy that gets remaining from that trade-off, it's what's going to be remaining in your system. So it's important to measure it because if it's too large or too small, your system will tend to go to a certain place or another. Basically, is it going to proceed or not? So it's very useful in chemistry or while analyzing your process to make it much easier to proceed than others, for example. So basically, it's a trade-off between enthalpy and entropy. And that remaining energy, it's quite useful because it could be quite large or small. So in this case, we want to know when that delta G tends to be larger and negative because it would proceed much better than the other ones and tend to be much smaller and positive. So here we have two cases where in the first one, the delta H it's quite negative, and the second one it's positive. But even though the second term is quite positive, having that negative term in here will make it negative, and the total delta of this Gibbs free energy will be negative. And if it's very large, it's quite good because then you can say that the process can proceed quite easily. And the second one, we have that if delta H is quite positive and the entropy decreases, it won't be enough to be larger than this term, so it will be much more positive in this part. And basically your delta G, your remaining delta G, will be quite large and positive, so that delta G won't be quite useful for a process to happen quite easily and fast. That's going to be spontaneous. So having this in mind, we always want to know as engineers how spontaneous is it going to be. Maybe you want it to be quite fast. So in this part, you analyze having certain variables, how are your molecules are going to start to move, and how many remaining energy are you going to have for it to proceed. So in here, we have certain cases that we want to analyze according to the equation. So in the first term, we have that, for example, if delta H is quite negative and delta S is quite positive, this will always tend to be spontaneous because being it positive, if you already have here a negative one, negative by positive will always be negative. So basically your final delta G will always be negative and therefore spontaneous. And the second one, both terms are quite positive. And in here, you may just depend on the temperature. Being it quite large, you have in here an uncalibrated equation from that side. So being your temperature quite large will increase your entropy in that side. So the delta G would tend to be spontaneous depending on your temperature. On the third case, both are negative. And in here we have a problem because, for example, if in here it's larger than this term, then it seems like this term will be much more positive as you have negative and negative signs in that side. So it would depend also in temperature. Being that temperature lower, it will allow it to be much more spontaneous. And on the last case, we have a positive delta H and a negative term here. And here we also have a problem because being it always negative, it would say that it will be positive in that case. So both terms are going to become positive as a positive term for delta G. So your final delta G will be quite positive and will never be spontaneous. So that's not ideal news if you want your process to occur. So in here we have certain properties that Gibbs free energy can give you if you are revising your process. And always while developing a process, you need to establish certain variables like P and T, which are temperature and pressure. So in here for your basic delta G equation, we know that those are unmeasurable variables, and we need to pass it to those variables that are easier to calculate, like being it more determinate. So here we can state that this term can change from TTS minus SDT, and this one from that. So in here it's already derivated, but in here we have to derivate those terms, and by substituting and reducing it both terms in the same equation, we find that our delta G becomes BGP minus LZT. And please note that in here, this first equation that we used to work on the previous slide has now become a more easier one in which we have known variables like volume, pressure, entropy, and temperature, and they are much easier to manipulate to understand what's happening in your process. So in here it gets reduced to the cases where you have constant pressure and constant temperature in your system, and you might want to know how are both going to behave. So in here we have your Gibbs free energy varying T, while pressure gets constant, which depends on entropy. And in here the Gibbs free energy varying the pressure while T gets constant, and it's proportional to your volume. So please note that this comes from that equation, having certain P and T constant, how are they going to behave? And where does that easier terms come from? Because it's very useful. You can apply it in many other equations to make them easier. And in here we have to talk about Maxwell relations, which are very useful in engineering because they relate measurable variables to measurable ones, as we saw previously, from enthalpy to, for example, volume and pressure. And here it basically comes from their partial derivatives, that which all here having a certain function and given certain variables. You go to this relationship, and here we have the canonical function for example, partial derivatives for two variables in a given function. Here we have x and y, and this term is what we use in here from the previous one. From here, it's what we used to reduce this to this and state it in two cases where you can have pressure or temperature constant. So it will be easier to study your case given certain pressures and temperatures being both in equilibrium, because it's just valid when you can state certain conditions that make it easier to understand what's happening in your process. And this is going to be quite ideal, but it gets easier. So in the previous case we saw that Maxwell relations. So here it's just a brief example of how does it change, for example, in internal energy to reduce it to measurable variables. So getting back to what we were seeing as the properties of Gibbs free energy, we have the temperature. So we want to know how is it going to vary according to your temperature. So for this case, we are going to take just one um, side of the equation where we have the change of Gibbs free energy according to temperature while having pressure constant. Why? Because it gets much easier to understand it, and because you can move all these variables at the same times in these calculations. So having this term in mind and the canonical Gibbs energy equation, we can solve it for T as we have in here. So solving for T and applying those Maxwell relationships with constant pressure, varying your temperature, you can get to this equation where you just know how to Gibbs free energy changes with entropy and your temperature. For the second case, we have pressure, and here we have to know that how is it going to behave when varying pressure having the temperature constant. So in here, as P is variable, we have it over here of our Maxwell relationship. So delta G will be equal to VdP. So it gets reduced and it gets easier. But here we have two cases. The first one is when the volume remains constant. And here we're talking about solids, liquids, which as you know are uncompressible. So maybe the difference will be there will be a certain difference, but it will be quite small that can be not considered. So here we could state that from this equation you can take B as constant. So in this case you can integrate taking B out of the equation and it reduces to a very easy equations from finding Gibbs free energy while pressure changes. But in the second case we have non-constant volume, and in this case are gases, because depending on the temperature they are going to increase or decrease their volume. So in here the delta G cannot be reduced to that equation because volume remains inside of the equation. So we need to pass it to, as we did for example in Maxwell relations, to something that is known. So in here we use equation of state. And here we use the basically one because as we're explaining there's like all ideal. So in here we have the ideal gas equation which is stated in here where we have PP equals to nRT. For this we can note that we can solve this for B having all the terms of something that you can take out of your equation because it has in here the P variable that is going to be integrated and you can take out R and T. But in here that N it can be taken away as all of your variables as R and T, all those are in your thermodynamic tables are stated as specific. So there's no necessity to add the N of the equation and it can be removed in here. So our delta G gets reduced just to the integration of dp over p and taking this out. So for finding the delta G when the pressure changes, we just have to know that it reduces to the RT and the natural logarithm of the both pressures that are present. So in here please be aware of the units of all those variables to get the correct ones in your tables. Finally, I want to talk about a little bit about those applications that Gibbs free energy can give, because you cannot stay just with what's given, for example, in thermodynamics, because it's quite interesting what can you get from it. For example, in chemistry, Gibbs free energy is used to measure a reaction process, and in here you can note a graphic which states the reaction process according to the free energy. And here we can state, for example, a reaction having certain reactants and certain products in the right side. So in here we want to know, according to adding certain catalyzer, how is it going to behave. And in here please note that your Gibbs free energy gets reduced using a catalyzer. So for an engineer in a chemical process, it is very useful because it can reduce the time and make it much easier. A second example is in biology, for example in metabolism and energy, where knowing gives free energy for the production of your energy in the cells. It's very useful for glycolysis, which is a process in which you get energy for your cells. So those are very important applications. I could mention much more, but they are very useful to understand the importance of Gibbs free energy, not just in thermodynamics.